Black holes, among the most perplexing and singular phenomena in the cosmos, continue to captivate astronomers and theoretical physicists with an intensity that matches the mysteries they embody. These celestial enigmas, defined by their immense gravitational pull and complete absence of electromagnetic radiation, mark a boundary beyond which the established laws of physics cease to function. Initially postulated by Albert Einstein in 1916 as a corollary to his general theory of relativity, black holes remained theoretical constructs for decades until technological breakthroughs in the 20th century enabled indirect observation. A pivotal moment came in the 1960s when astronomers studying the Cygnus star cluster detected an anomalous celestial object, a bright, azure-hued star emitting intense X-ray radiation. This star was observed to orbit an invisible companion whose mass and behavior could only be explained by the presence of a black hole, later designated Cygnus X1. The confirmation of Cygnus X1 offered the first solid evidence of black holes' existence and ushered in a new era in astrophysical inquiry. Located roughly 6,000 light-years from Earth, Cygnus X1 possesses astounding characteristics. Despite its relatively small size, it exerts gravitational forces so powerful that even photons, particles of light, cannot escape its grasp. This defining trait led to the apt name, black hole, capturing both the physical properties and the conceptual darkness surrounding these entities. Subsequent astronomical investigations have uncovered a broad spectrum of black holes scattered across the cosmos. Estimates suggest that our Milky Way galaxy alone may contain over 100 million of them. These range from stellar mass black holes, formed from the collapse of massive stars, to supermassive black holes residing at the centers of galaxies. Despite their elusiveness, astronomers have identified numerous black hole candidates by observing the behavior of surrounding matter and detecting gravitational effects that reveal their hidden presence. Black holes wield influence far beyond their immediate vicinity. They play a significant role in shaping cosmic structures, regulating the formation of galaxies, and affecting the motion and fate of nearby celestial bodies. Matter that ventures too close is inexorably drawn toward the event horizon, the ultimate boundary, where it is subjected to extreme tidal forces before being consumed by the singularity at the black hole's core. This violent process, often referred to as spaghettification, vividly illustrates the immense strength of a black hole's gravity. As an object approaches the event horizon, it is stretched and compressed by gravitational differentials until it forms a long, thin filament resembling spaghetti. Although black holes provide natural laboratories for studying the extremes of physical law, they remain enveloped in mystery. The quest to understand them is fueled by the deeper ambition to unlock the very nature of space, time, and gravity. Across the vast expanse of the universe, these silent sentinels compel humanity to venture into the unknown, daring us to extend the limits of knowledge and perception. Despite the enormous distance between Earth and even the nearest known black hole, approximately 1,500 light-years, public intrigue and scientific concern persist. In 2021, a landmark achievement in astrophysics was realized when scientists unveiled the first direct image of a black hole, located at the center of the M87 galaxy. This extraordinary image offered unprecedented insight into the structure and dynamics of black holes, overturning simplistic notions of them as mere voids. Careful analysis of the M87 black hole image revealed a surprisingly complex structure. Scientists identified three key layers. The outermost is the event horizon, the point of no return where gravity becomes inescapable. Just inside this lies the photon sphere, an unstable orbit where light is trapped, circling the black hole indefinitely. At the core lies the singularity, an infinitely dense point where the known laws of physics break down, plunging researchers into realms of profound ambiguity. Each black hole, while sharing this fundamental three-layer architecture, displays unique properties that defy easy classification. As a result, traditional scientific methodologies often fall short in fully deciphering these exotic entities. Because no information or matter can escape from within the event horizon, direct observation is impossible. Any probe sent inward would be destroyed. Consequently, researchers rely on indirect observation, gravitational lensing, X-ray emissions from accretion disks, and gravitational wave signals generated during black hole mergers. Theoretical frameworks for black holes have evolved significantly. Some of the most compelling theories relate to their formation and internal structure. While stellar collapse remains the primary mechanism for stellar mass black holes, supermassive black holes pose greater challenges. NASA's studies of M87, for example, offer compelling evidence that such giants exert gravitational influence across entire galactic cores. In 1963, physicist Roy Kerr introduced a groundbreaking model of rotating black holes, now known as Kerr black holes. Central to his theory is the ergosphere, a region just outside the event horizon where spacetime itself is dragged in the direction of the black hole's rotation. Within this peculiar zone, classical physics begins to falter, hinting at unknown dynamics operating at the heart of black holes. One of the most provocative implications of Kerr's theory was the theoretical possibility of wormholes, also known as Einstein-Rosen bridges. These hypothetical tunnels through spacetime could, in principle, link distant regions of the cosmos or even serve as portals to alternate realities. According to general relativity, spacetime behaves like a flexible four-dimensional fabric that can be warped by massive objects. A wormhole could act as a shortcut through this fabric, enabling rapid transit between 2 points in space. However, despite their allure in science fiction and theoretical physics, wormholes remain speculative. Issues of instability, quantum fluctuations, and intense radiation make their practical use for interstellar travel highly improbable. Moreover, Einstein's theory of relativity imposes fundamental limits on the speed of information and matter through spacetime, further complicating any dream of faster-than-light travel. Still, the concept of wormholes symbolizes the bold imagination and relentless curiosity that drive scientific exploration. The pursuit of a theory of everything, a framework that unifies all fundamental forces and particles, has energized efforts to reconcile general relativity with quantum mechanics. Among the leading candidates in this quest is superstring theory, which posits that the universe's basic building blocks are not point particles, but tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to the variety of particles and forces in nature. Within the superstring paradigm, the universe becomes a grand symphony, with each particle a specific harmonic of an underlying vibrational pattern. One of the theory's most remarkable implications is its potential to explain the extreme behaviors associated with black holes and other exotic phenomena predicted by general relativity. As strings move through space-time, they create distortions, singularities, and complex topologies that may underlie the observable universe. Yet, superstring theory carries profound theoretical demands, particularly the requirement for additional spatial dimensions. While we experience 3 dimensions of space and 1 of time, string theory necessitates up to 10 or 11 dimensions, most of which are thought to be compactified, curled up so tightly that they remain imperceptible. These hidden dimensions challenge conventional intuition but offer elegant solutions to lingering cosmological puzzles. To illustrate these ideas, physicists often turn to analogies. Imagine a 2-dimensional fish pond where the fish cannot perceive the 3rd dimension of air above. Similarly, we may be unaware of dimensions curled tightly around us. These compactified dimensions, though invisible, may shape fundamental forces and particle interactions, offering deeper insight into the universe's structure. Superstring theory has also revitalized mathematics, uncovering deep connections between abstract mathematical frameworks and tangible physical phenomena. The ongoing pursuit of a unified theory has fostered interdisciplinary collaboration, revealing the harmony between mathematical beauty and scientific truth. Despite its conceptual appeal, superstring theory remains experimentally unverified. The energies required to probe these extra dimensions far exceed current technological capabilities, confining the theory largely to mathematical speculation. Nevertheless, the elegance and ambition of superstring theory continue to inspire physicists, mathematicians, and philosophers to push beyond the known frontiers of thought. Among those captivated by these possibilities is physicist Michio Kaku, whose contributions to superstring theory have brought its complex ideas to broader audiences. He describes the universe not as a static entity, but as a dynamic, interconnected whole shaped by invisible dimensions and vibrating strands of energy. Recent progress has brought fresh optimism to the field. Edward Witten, one of the foremost minds in theoretical physics, famously described superstring theory as 21st century physics that fell into the 20th century. His optimism is echoed by new developments suggesting that quantum black holes might be modeled using simplified two-dimensional versions of string theory, an unexpected breakthrough in a field known for its towering complexity. Although much work remains, these advances hint that we are inching closer to resolving some of the universe's most confounding mysteries. As researchers continue their quest to understand black holes, objects that defy categorization, consume matter and light, and perhaps even bend the fabric of reality, we are reminded of the limitless power of curiosity. The study of black holes transcends mere academic interest. It represents a fundamental challenge to our understanding of existence. Their interplay with neutron stars, gamma-ray bursts, and the structure of galaxies reveals a web of cosmic forces and interactions too vast to ignore. In every effort to explore them, we draw nearer to answering the age-old question: what is the true nature of our universe?